tonight or tomorrow or the next day if you use late days. Any questions, problems? Yes?
If we submit a successful solution on Caddis with a certain programming language, but we want to try other ones, but we don't get it to work, will we still be okay grading-wise?
Okay, so he's asking what happens if you continue submitting Caddis problems after you've submitted the one that works? Can you ruin your grade that way? No, what we do is we look for the one that gives you the highest grade that was submitted before the deadline. So yeah.
So our grade is based on test passing only and not on time performance, to the extent that it doesn't pan out?
That is correct. All that matters, if you pass all the tests on Caddis, that's what we look at. We just look at the test on Caddis. Yep.
The tests, are they your tests or are they like from Caddis?
No, the tests are just the ones that you see on, when you run it, you see there's like, I don't know, 10 test cases.
Well, I'm just wondering if like you wrote those or if they...
Oh, did I write them?
Yeah.
Yes. This particular problem I wrote. So this semester, a little over half are my problems that I wrote, and the rest are ones that were already on Caddis.
Okay. I found an edge case that was tested. I don't know if you want to know that.
Sure, let me know. I won't change it this semester. Yeah?
So in terms of late days, is one problem considered like PS1-1, or
Yes.
is each of those problems?
Yeah. So,
Okay.
so if you tanned everything in tomorrow, that would actually be 4 late days because the Caddis problem's not due tomorrow. Actually, I take that back. There's 2. Also, the analysis problem isn't due tomorrow either because of Caddis, but yeah. It's 1 late day per. PS1 is 1 problem for that purpose. Other questions? Okay, well, then tomorrow the next set of problems will come out and we'll be rolling until that way until the midterm. All right, this is what we ended up last time with this asymptotic complexity plot here. And we showed that the blue function is O, well, let's say that the red line is O of the blue line, but also the blue line is O of the red line. So what's the simple argument that the red line, which is G of n, is O of F of n, the blue line? What's the argument? This is the simplest case for formally proving big O properties. Yeah.
Is it because f of n's end behavior is constant?
Well, he said it because f of n's, he's saying it's because f of n, the blue line tends to a constant. That's that's our rule of thumb, yeah, but that's not that's how you recognize it, but it's not how you prove it, I guess I'm saying. What does he have to show? Yeah.
So G of n's upper bound on the worst case is less than or equal to 1 over n plus 2. So it's typically O of n, or O of f of n.
You're saying G of n's, well, you see G of n is just constant, so best is just one case.
Right. So big O of n is, or big O of f of n is less than or equal to, so it's technically true, right?
Well, but again, what is it? What property does the blue line have that lets us conclude immediately that the red line is O of the blue line? Yeah?
The blue line's always above the red line.
That's it. The blue line's always above the red line. A function that is larger everywhere than some other function definitely bounds at the rate of growth from above. Okay? So if you've got a function that's always bigger than some other function, then the smaller function is O of the bigger function. Okay? That's a basic fact. But we can also show that f of n is O of G of n, even though G of n is always lower. Because big O doesn't have to do with magnitude, it has to do with rate of growth, with doubling behavior. Okay? So how do you prove that the blue line is O of the red line? Yeah?
You can multiply the red line by some constant to make it so that it's always greater than 2.
Okay, you can multiply, the proofs involve multiplying, in this case, the this function here, the red function, by a constant to try to get it above the blue line. Now, remember, big O has to do with rates of growth or doubling behavior. Multiplying by a constant doesn't change the doubling behavior of the function, preserves it. So can we multiply the red line by a constant to make it higher than the blue line everywhere?
Not necessarily everywhere.
Yeah, this one you can, not everywhere, because no matter what constant we multiply it by, if we get close enough to 0, the blue line is going to be higher because it's tending toward infinity. Multiply this by 1,000,000. You squeeze close enough to the y-axis, the blue line is going to blow past the red line. Nevertheless, we can prove that blue line is over the red line. So what's the other aspect of a proof of big O-ness? Yeah.
You can decide a cutoff point and ignore the left half of the curves, so you
Right.
only care about the right.
Okay. You can pick a point on the x-axis and just ignore everything that happens to the left. And just pay attention to the right. So now the question becomes, can you pick a point in the x-axis, let's say this one, so that, and then find a constant you can multiply this red line by, such that the red line will be above the blue line all the way to positive infinity. And anywhere you pick will work. The further to the right we pick, the smaller the constant has to be. But, I think we said that, what is it right here? It's like 2.5 right here maybe? So if we just multiply this function by 2.5, it's going to be bigger than the blue line to the right of 2. That's what every formal proof of big O-ness looks like. That's a term I just coined, big O-ness. But it involves finding those two constants. And they're not unique. We could so n naught is the part of the x-axis that where you're starting looking. In fact, you could pick anything as n naught, and then pick almost anything as your constant, as long as n naught's positive. So that's the game when you're doing these formal proofs. Now, informally, what we do is we just observe that they're both constant in the long run. Their high order terms are the same type of thing. The high order term is a constant. That's a high order term here, that's a constant, that's a constant. So they're both O1. Okay? So here is, we saw this table before. You remember there's little o, big O, theta, big omega, little omega, that correspond to these bounds, less than, or equal to, greater to, or greater than, on rates of growth. And if you're interested, here's the formal definition of each of those. Like here's big O, is the only one we looked at. Now, I don't care too much about little o and little omega. We don't use them much. And how would you prove something is theta of something else? Suppose you're the world's greatest expert on proving that one function is O of another function. How could you use that expertise to prove that some function is omega of some function? Yeah?
You mean prove it's theta of omega?
Omega.
How prove it's omega? You just prove the reverse one, so you prove the other one.
Okay, you just reverse. If you want to prove f is omega of g, just prove g is O of f. So you just switch the roles. You turn upper bound, lower bound to upper bound. And if you were the world's best prover of big O proofs, how would you prove something is theta of something else? Yeah?
If a function is a big O into another function, and that function is also a big O.
Right. If you want to prove f is theta of g, you prove f is O of g, and g is O of f. So if you could do big O, you can do both of these. And these I don't care so much about. So that's the one that matters. We want to prove that f of n is O of g of n. Then we find these two constants such that 0 is less than or equal to f of n is less than or equal to c times g of n for all sufficiently large n. And that's the bottom line. So it's actually not hard to do. Let's look at an example. I want to prove that 5n squared is O of n squared. So this is 5n squared. And this sort of yellowish green thing is n squared. So I want to prove that red line is O of yellow line. Doing it informally, we just say, oh, throw away the leading constant, done. But what justifies throwing away the leading constant? That's when you have to use the definition. So ignore the symbols up there for the moment, just looking at the graph. What would be a graphical proof? Yeah.
Maybe if we could bound it above and below with an n-squared graph.
Well, we don't have to bound it below, we're doing big O, just above. But the proof, what you've got to do is come up with a constant C and a constant N naught, such that that property on the last slide holds. So just viewing the graph, what do you have to multiply this by to get it to get at least as big as the red? 5. And then what will work is N naught? 0 would work. Anything would work. Because it's going to be the same curve. So that's a fine proof. You just appeal to the graph. You say, okay, that's the red curve. This is the yellow curve. If I multiply this curve by 5, I get the red curve. It's positive. It's positive. At least it's not negative there anywhere, and it's always the same. Yeah.
Would it be okay to take the derivative of either a line?
Well, what would the derivative tell you?
Well, the rate of growth, I would believe.
How fast they increase.
Yeah. You could probably justify taking the derivative by appealing to the definition right there. You can consider that. Okay. Yeah.
Given the correct range, could even something that's O of n cubed also be O of n squared if you just shorten the range?
You're saying, suppose this red thing were an n cubed,
Right.
could it be O of something that's n squared?
If you shorten the range so it wasn't all real numbers.
Well, you can't shorten, when you pick an n naught, you're not saying ignore everything in this direction.
Oh, that's right.
You're saying ignore everything in this direction. And no matter, you multiply n squared by the world's largest coefficient, a lowly O to n cubed curve will eventually pass it. That's just, we talked about that when we talked about orders of growth. Now, let's talk about doing as opposed to a graphical proof, which is perfectly fine. The problem with the graphical proof, it's a little hard to, it's fine to talk to someone and explain it. It's a little harder if you're doing an assignment and you got to hand in a proof to argue using a graph. So let's try, working more symbolically. Okay, so you see my proof written up there on the slide. Let me just try to reproduce it down here so you see what I'm doing. So we have to find constants so that 0 is less than or equal to 5n squared, which is less than or equal to cn squared for sufficiently large n. So we need to find an n naught such that that's true for every n greater than or equal to n naught. So can we divide through by n squared? Okay, then I take n squared and divide all three of these terms without screwing up the inequalities. Remember, you have to be careful about that. Okay, any restrictions on the value of n? Can't be 0. You can't divide by 0. Could it be negative? Well, if I divide, okay, so if n is negative, divide by n squared, that'll be okay because n squared is positive. Got to avoid dividing by a negative number. So I'm just going to assume that n is greater than 0. That rules out 0. And when I divide by n squared, I get 0 less than or equal to 5 less than or equal to c. So is that true? For what c's is that true? For any c 5 or greater, it's going to be true. And what do we assume about n? Just that n was not 0. So the assumption we made about n in doing the proof gives you the n naught. N naught, in this case, for this proof, n naught can be any positive number. And c has to be less than or equal to 5. Okay? When you get an assignment, I think my problems are even easier than this. I think on my assignment I'll do something like, I'll give you an n naught and ask you what's the smallest c. Or give you a c and ask you what's the smallest n naught, or something like that. So there's only one thing to determine. So that's sort of your basic proof of that something is bigger than another. It's just trying to find a constant in n naught. And you can do it by looking at the graph and arguing that way. You can often do it just doing some algebra. Yeah?
So in this case, can we choose n naught to be 0? Or?
Well, this proof doesn't justify you choosing n naught as 0 because we couldn't have done this division step if n is 0. Now if I change this to greater than instead of greater than or equal, which really wouldn't matter, then I could use n naught as 0. But technically for this proof you need n naught to be any positive number. Yeah?
Sorry, this hasn't quite clicked for me. What if I were to choose 4 as my constant? Would that invalidate my proof?
Well, this inequality is not holding anymore. This says I have to find a C, so for this inequality to be true, which is what we have to prove, this inequality has to be true. For this inequality to be true, C has to be at least 5. If you plug in 4 for
okay.
C, you've got false.
I see where I didn't parse that correctly. Thank you.
And then once you decide C has to be at least 5, you have to go back and ask yourself, what did I assume about n to get here? And that tells you your n naught, your minimum n naught. Any other questions? Right, we'll do a couple more. Closing the right thing here. Hey, what about this one? I want to prove that 5n is O of n squared. Okay? So this is 5n, the red line, and there's the funny looking yellow line. Yeah?
If you just choose the right n naught, we can see right now that it's going to be less than.
Right. So you can see they cross at 5, right? If you ignore everything that's going on to the right of 5, then by the time we hit 5, it's clear that the n squared curve is above the 5n curve from the graph. Yeah?
Is there any point in choosing 5 as opposed to just 100?
No, there's no... You can choose anything as long as it's 5 or greater.
5 would be the tight round, right?
5 would be the smallest you could use, yeah. Well, no, I take that back. What if you wanted to use 4?
You would have to multiply.
Change the constant?
Right, we could use a smaller c if we used a bigger n naught. I mean, imagine we said n naught is 100, or 10. Suppose we said, okay, let n naught be 10. Oh, we were talking about n naught, I'm sorry. What constant were we using here? We said if n naught is 5, if n naught is 5 or greater, it's obvious, but what value of c are we using when we do that? 1. So if we used a different value of c, we could use a smaller n naught, right? Let's suppose we let n naught be 2, then c would have to be, I don't know,
0.5.
or we'd have to multiply this times something to get bigger than 10. Let's just multiply this by 10. Clearly that would be bigger. So you could use an n naught of 2 and a c of 10. That ought to work. Yeah?
Is there any value to trying to solve for a smaller n naught, or is this just if you can get this condition satisfied anyway?
Yeah.
See any n naught?
You get the condition satisfied anyway, you're good. All right? Let's push it through in symbols now. So again, what I'm going to do is I'm going to say, okay, we have to show that 0 is less than or equal to 5n, less than or equal to c times n squared. So we're going to solve for e, and we're going to keep track of what assumptions we make about n. Okay? So what I want to do is divide through by n squared again. So you've got to make sure n is not 0. So 0 less than or equal to 5 over n less than or equal to c. Okay, but we still got that annoying n, that n in the denominator there. So how can we cope with that? Got an idea?
Factor it out.
Well, we can't really factor it out because it's the only one there. Yeah?
Well, if you assume n is positive, then you can never get greater than 5.
Well, he's saying assume n is positive, then that term will never be greater than 5. The problem is n could be like 0.00001. But what if we just assume, what if we assume that n is greater than or equal to 5? If we make that assumption, what do we know about that term right there, 5 over n? It's got to be less than or equal to 1, right? If n is greater than or equal to 5. So that reduces to 0, less than or equal to 1, less than or equal to c, assuming, of course, that n is greater than or equal to 5. And that's going to be true for any c greater than or equal to 1. So that gives us a minimum c of 1, as long as our n null is 5. Yeah?
Is it equally valid to pick your C value first?
Sure. Yeah. You could pick a c value and then solve for n. That would work. But I just know from experience that when I assign these things, I get lots of questions from people asking, they think there should be a unique answer, but there's not. Yeah.
So I'm perfectly fine to pick, but it's a good rule of thumb then, to pick my denominator to match my numerator, or my...
Your dot, what do you mean? You mean the step right here, 5 divided by n?
Yeah.
Well, I just got to figure some way to put a bound on c. And so I just observed, okay, if I make n big enough, this will be 1 or less. Or I might have said, if n is greater than or equal to 10, this is going to be less than or equal to 0.5, and then c could be 0.5. Doesn't matter. I just got to find, I make some assumption about n that turns this into a constant, so I got a value for c. Yeah?
Do we have to stick to multiplying by the constant, or should we just add it and solve it that way?
Add what?
Add c instead of like n squared plus c rather than...
No, for the definition, you need to be multiplying the big O term by the constant.
Okay.
Yeah?
Could we just pick values for C and not before the image?
You could pick values for c and n naught, and then just show that when you make those assumptions, the inequality holds. That's correct. Yeah?
Is there a reason why we compare both equations to be greater than or equal to 0?
Okay, so he's asking about this here. That's just part of the definition of big O, that we're only interested in positive things. But that's not at all a problem with how we're using big O, because we're using big O to measure either running time or space consumption, and that's never going to be negative. Okay? Let's look at another one. So I want to prove that the log base 2 of n is O of the log base 4 of n. So this is log base 4 of n. It grows more slowly than log base 2 of n. To make a long story short, there's a property of logarithms up there. Log base a of n is equal to log base b of n divided by log base b of a. So there's a way to convert between them. You can show that this curve here, the blue curve, is just twice the red curve, just using an identity of logarithms. So if we multiply the red curve by 2, we get the blue curve. So we use a constant of 2 or bigger, and any n naught will work. Well, I take that back. Why won't any positive n naught work in this case? Yeah?
Is the logarithm value just goes negative?
Right, it becomes negative before 1, it's negative. And we can't have negative, we got to have that 0 at the beginning. So our n naught needs to be at least 1 to deal with the negative case. So that's just using a logarithmic identity. And one last one. I want to prove that n squared plus 5n is O of n squared. So this is n squared, and this is n squared plus 5n, which is a little bit higher. But in the long run, they grow the same, right? The doubling behavior is the same. You double is n, you quadruple the value. So once again, sort of the same idea. I just take the inequality, I divide through by n squared, I make an assumption about n that puts a bound on that 5 divided by n term. And I come up with c equals 2 or n naught equals 5. Or someone else says, you could just say, okay, what if we make C be 100 and we make N naught be 10? You could just guess and plug in and see if it works. So it's really not a hard game to play. It's just these inequalities, and you get to pick the constants. Okay, so that's what I had to say about. In fact, there we go. I actually have that animated. I multiply what I use for my constant 2. If I multiply that curve by 2, I get that. So basically, we're just up there. We're just solving for this intersection point when C equals 2. And that becomes our N naught. So any last questions I could answer about this? I know they won't be the last questions I answer about this, but they might be the last ones I answer today. So. Okay. Well, let's talk about something else. So 2420 is largely a course about basic algorithms of data structures. And for data structures, it's things like lists and sets and maps. So we're going to do a quick review of lists right now, and then maybe look at an aspect I'm not sure if you looked at 2420. Perhaps. We might all be reviewed. So this is what I mean by a list. It's a collection of elements indexed with integers. So think array list, think linked list, whatever. Lots of kinds of lists. There's going to be a method that allows you to get the value stored at a given index, or to change the value stored at a given index. There's going to be a method that lets you add to the end of the list or remove from the end of the list. We're going to assume that there's a way to iterate through the list. And we're also going to assume that as you're iterating, and you're at a certain spot, so as soon as you've iterated over and you're in the middle of the list, there's going to be an operation that allows you to get the value stored at that point of the list that you've iterated to, or to set it, or to add a new element before or after that spot, or to remove the element at that spot during an iteration. So any list thing, any list, lists, array lists, and linked lists in Java or C# have this property. As you're iterating through the list, if you're iterating the right way, you can modify the list at the point of iteration. You can't do it with a for each loop. You have to use an iterator object in Java. Okay, that's what I mean by a list, by the list abstraction. Okay, now let's look at two common representations of a list. There is what I call dynamic array representation. So this is how array lists work in Java. You have internally inside the list object, you have a fixed length array. But at any given point, there's room to grow. So for example, what you see up there at the top is a list, is an array list, and what is the length of the array list? This is the internal representation of the array list. So what you're looking at there is an array. What's the length of the array list that this represents? 6. There's 6 elements in the array list. 5, 8, 2, 3, 7, and 5. And there's room for 4 more in the future. But if you're just a client of the list, you don't care that there's room for 4 more or whether there's room for 100 more. You just care that you can access those 6 elements. So that's just behind the scenes. And there has to be, so because of that next point, you have to also have an instance variable that holds the 6, that tells you how many of those elements of the array actually matter. And then when the array fills up, what you do is you say it's full and you got to add a new element. There's nowhere to put it. So at that point, you allocate a new array that's twice as long as the old array, copy the old elements over the new array, and then throw away the old array. And the new array becomes your representation. So you get lots of efficient adds, and then at some point there's an expensive add when the list doubles, and you got to copy. And then you get a lot more inexpensive adds, and then finally another double. Turns out that's way more efficient than just reallocating the array each time it fills up and adding room for one more spot. So that's what I mean by dynamic array representation, array list in Java. So let's analyze it. What is the best case for a get operation? So you're just given an index, you say, give me what's at this index, yeah?
Index 0?
Well, I mean, using big O notation.
Constant.
Constant time. And in fact, it doesn't matter if it's index 0 or index 5. Since that's an array we're indexing into, it's constant time. What's the worst case? I just said that. So they're both, in both cases, the best case and worst case are all constant. Okay, what about adding to the end in the best case? Constant time. If there's room to grow, if there's still room to grow, like adding another element to the example up top there would be constant time. You just plop it in the next available spot. What's the cost of adding to an n-element array another element? An n-element array list, another element. Right. If there's n elements, the worst case is all n elements are occupied. The array is full, and you've got to double it. So you've got to copy all those elements over. So that's going to depend on n. So that's proportional to n. So in the worst case, it's a linear time add last. So if you timed it, you get fast, 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 slow, fast, 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 slow, even slower. Each time it doubles, it takes longer and longer. What about iterating over a list? So you got a list and you iterate over it.
That would be constant.
Well, no, not constant. Yeah, that's linear time as well. The time it takes to iterate through it depends on how long it is. Now, you're iterating through it and you've gotten to a spot. You've got your finger on one of those things. What's the cost of doing that get operation? Yeah, that's constant. And what about the cost of adding an element at the spot in the worst case? I'm sorry, in the best case. What would be the best case for adding at the iteration point? You happen to have iterated all the way to the last element, and you're adding at the end. So in the best case, that would be constant. In the worst case, what would be the worst case? Adding at the beginning, even if there's room to grow. Add at the beginning, because you got to shove everything over one, makes room, to make room for the new guy. So that's linear. Okay? So that's that. Then there are linked lists. Suppose we have a doubly linked list now. And the idea is that each element points to the one before it and after it, and that we also maintain a reference to the beginning and to the end, so that we can get to either end quickly. And to insert just takes a little bit of reorganization. We just plop a new element and adjust some references. Yeah? Mm-hmm.
You said that get at was constant in the best and worst case.
If, say, what was?
If get at operation
Yeah.
is constant in the best. Don't you have to run through the list and get to the point where you
Yeah, I'm not counting the cost of the iterating in that. We've already paid the price of getting to the spot.